Hello, my name is Chuck Brokish from Green Hill Software. Today we will be talking about solving multi-core interference for safety-critical and security-critical applications. So why am I here presenting today? I don't want to make this a marketing pitch, so I'll just say that as a company, Green Hill Software has been in business since 1982 and has developed solutions for some of the most security-critical and safety-critical systems in the world. Among these solutions is how to address multi-core interference for these safety and security critical systems. These solutions not only meet the most stringent of standards in many industries, but set the bar at the highest level in such industries as aerospace standards for multi-core interference mitigation. Within almost every industry, we are seeing more use of multi-core processors. There are many factors driving this trend. There's increasing complexity within the applications, which demands more compute power. There's an increasing number of compute engines within systems as we migrate capabilities to more software control. As these processors continue to add up, there's a desire to control the cost and power of such distributed systems and consolidate many of the functions into fewer multi-purpose compute units. And of course, as we need more compute power, we are seeing that Moore's law is reaching a threshold and giving way to simply adding more cores. As evidence of the points just made, we can see that over time, the code size of almost all applications, embedded as well as IT, continues to increase as more capabilities are added. With this increase in code size and function, we also see the need for more compute power. The green dots of the graph to the right demonstrate the flattening of compute speed as Moore's law is reaching a threshold. To make up for this, as can be seen by the black dots of the graph, the industry is adding more cores to the devices to continue increasing that net compute capability. If we look at a couple examples, such as aerospace and automotive, we can see many of the compute capabilities that have been designed into the systems over time. But we also see an evolution from adding more discrete compute systems to then consolidating those capabilities into centralized compute clusters. These consolidated compute clusters are demanding far more processing capability than can be handled by traditional single-core solutions. So let's take a look at what is driving distributed versus consolidated compute within the various industries. But let's do so from the perspective of the SoC. So let me start by clarifying that I want to consider consolidated compute of diverse applications on the same processor. When we think of high levels of consolidated compute, our tendencies are to think of large servers, such as web servers and network servers with extreme data flow. But I'm not talking about large banks of hundreds or thousands of processors all doing the same operations in parallel. Rather, I want to think of processors that are performing diversely different tasks, but on the same processor, looking at it from the perspective of the processor, or the SoC. Our initial thought might be that the cloud and network servers are great examples of consolidated compute. This may be the case from a geographic perspective, but if we look at the systems from an SoC perspective, we can see that while such systems may be centrally located, they are actually distributed compute. Cloud services and network servers do make use of multi-core parallel processing, but they use many processors to accomplish these tasks. And any given processor is likely doing multiple instantiations of the same process, all running at the same priority and at the same recurrence. Edge computing is becoming a larger market space within IoT and has become a requirement for many systems that cannot tolerate the latency involved with waiting for a response from the cloud. While they make use of cloud services, much of the computation is distributed at the edge of discrete devices outside of the cloud. And of course, thermal is always a concern on high intensity compute needs, which often dictates distributing the computation over many devices for the sake of heat dissipation. So these types of systems are simply distributing the various compute needs over several processors, which are optimized for that specific task. On the other hand, we see that embedded systems are increasing the demand for consolidated compute. These systems are consolidating a wide diversity of capabilities, all into single high-performance compute engines. Embedded systems have very different requirements than IT systems, as they are often far more constrained by size and power. As demonstrated in the last slide, there is a trend to reduce components where possible in embedded systems. Size, weight, and power are always considerations within embedded systems. As systems continue to add more electrification, there become too many subsystems to develop and maintain independently. Additionally, many of these subsystems already share a lot of content. By using shared memory on a single device, the designer can reduce a lot of redundant reading and writing of shared content, as well as additional cabling needed to bus information between independent control units. So creating a consolidated compute engine based on a multi-core processor that can handle a wide variety of compute needs has tremendous advantages in these embedded systems. However, when migrating to these multi-core compute systems, there are limitations and considerations that must be tended to. The effective compute power is likely not going to equate to the number of cores in the system due to limitations in parallelization and sequential compute functions. And bandwidth considerations must be taken to address memory and bus contention as multiple initiators all try to access the same resources. The trends we see within SoCs today are to continue adding more hardware accelerators and task-specific processors. In addition, we continue to add more high-speed peripherals, which have high bandwidth requirements. The addition of many bus masters can create traffic congestion for the same resources. Such bus masters include not only the cores directly, but also cache mechanisms, DMAs, hardware accelerators, and external networks that have direct memory access, such as PCIe. Some of these initiators can create large bursts of data that can occupy large segments of the bus utilization, which can dramatically impact response latency for other initiators. With this trend toward multi-core devices, we see a lot of positive aspects. We get more compute power per processor, allowing higher concurrency and parallelization. It is possible to get by with less context switching if we can split multiple processes across multiple cores. There are cost savings from fewer processors in our end system. This comes not only from reducing the number of SoCs, but also fewer memory devices, as well as power management devices. And we get improved size, weight, and power for our end system. However, there are considerations to be taken into account within these multi-core devices. The effective compute power can be heavily dependent on the amount of parallelism possible within the system. And there is more bus contention to the shared resources, especially memory. But most importantly, we must consider the fact that we can see a loss of determinism, which can be catastrophic for safety-critical tasks if it's not properly addressed. There are multiple sources of interference running on a multi-core system. This can come from multiple applications running on the same core and potential interdependencies. It can come from independent applications running on separate cores, but using common resources. And it can come from applications that have threads distributed across multiple cores. There are several means of accommodating multiprocessing across multi-core devices. Perhaps the simplest is asymmetric multiprocessing, in which each core is treated as its own device, running its own software. This eases scheduling within the solution, but latencies are still affected by shared resources. This can also lead to inefficient use of the device, since some cores can be overloaded while other cores sit idle. Symmetric multiprocessing allows one to maximize resource utilization by enabling any task to be run on any core as resources become available. The caveat to this solution is that determinism can get complicated, since the same task may not run on the same core and in parallel with the same other processes from one iteration to the next. Bound multiprocessing uses core affinity to lock applications to specific cores. This prevents dynamically remapping applications across multiple cores and can remove some of the lack of determinism seen in SMP. It uses a mix of manual and automatic load balancing, depending on how the core affinity is assigned. Any manual load balancing within such a system may reduce the efficiency, much like we see in AMP. Time-partitioned multiprocessing allows the ability to blend AMP, SMP, and BMP. In this case, partition scheduling can be used to provide different operational modes depending on which time partition you're in. Many in the industries using embedded processing are looking at hypervisors to try to isolate critical and non-critical applications from each other, and hoping they can still ensure the safety critical and security critical aspects of the design. The sole purpose of hypervisor is to virtualize multiple operating systems in an attempt to prevent them from interfering with each other. But for critical applications, we need streamlined minimal software to enable real-time response. So if a hypervisor is running underneath the real-time operating system, the real-time response will be delayed. So let's take a look at Type 1 versus Type 2 hypervisors. Type 1 hypervisors have multiple schedulers within them, which remove determinism and real-time response for safety-critical systems. This loss of real-time response renders the RTOS to potentially no longer being real-time. Such systems were not developed or evaluated for safety or security and are often built in very large code bases. Trying to certify such a system for safety or security when it was not created for that is impractical from both a logistical as well as a financial perspective. They use core boundaries as a crutch for separation, and as we will discuss a bit later, debugging can be very challenging. These Type 1 hypervisors are often very large and have slower boot time to get to critical services. Because of the size and the fact that they were not developed with safety and security in mind from the onset, they create an increased cyber attack surface. This can be evidenced by simply looking at the increasing number of vulnerabilities listed on the National Vulnerability Database. As I've heard stated, using a Type 1 hypervisor to solve safety and security critical systems is like using a hammer as a surgical instrument. A better alternative is a Type 2 hypervisor based on a certified separation kernel. A certified separation kernel is evaluated for security and safety. It has better response time versus a Type 1 hypervisor. This solution shows better real-time performance versus a Type 1 hypervisor, and it makes debugging much easier as all of the applications can be simultaneously debugged from the same environment. By using a combination of mediated and pass-through devices, optimal performance can be obtained for the high-level OS while still ensuring that hard real-time deadlines are met for critical services. This also enables more flexibility to migrate applications into and out of virtual machines as system requirements change. Furthermore, as we will be discussing shortly, you lose the ability to mitigate multi-core interference on these multi-core devices because the Type 1 hypervisor does not have the real-time attributes to properly address this interference. There are many challenges when looking at system consolidation. SoCs are becoming not just a system on chip, but a system of systems. These systems have very diverse requirements, including items such as real-time response, safety requirements, security concerns, compute requirements, bandwidth requirements, etc. The applications on these devices have very different development environments and debugging methods. This can range from highly optimized drivers in low-level assembly code to compiled languages to object-oriented development. Debugging can entail something as simple as printf statements within a debug terminal, to debug log files, to low-level JTAG debugging, to high-speed parallel trace on every access of the device. And of course, synchronization of all of these activities and debug details can be overwhelming. Once developed, there is still the task of testing, validation, and certification. The benchmarking result of individual applications can change dramatically when running in parallel with other applications. Benchmarking goes beyond just CPU cycles, but also includes details such as latency of accesses and response times, memory bandwidth and utilization, and the crossbar and fabric utilization of the specific SoC being used. Profiling must be done to ensure proper operation of concurrent application use cases. Multiple independent applications, possibly developed by different groups, all have to be integrated into a single system. Apps that run fine out of context may fail when integrated. And of course, certification must be addressed at every stage of the development to be sure that proper measures have been taken to ensure the safety and security certification of the end applications. I mentioned earlier that debugging these complex systems can be complicated. If you look at the common debug mechanisms used to debug such systems, you'll see that there are many different tools used. These include low-level debug mechanisms such as JTAG to debug bare metal capabilities and to debug low-level boot operations of the system. Once the silicon is booted and low-level software is running, there are other methods used, including separate debugger consoles for virtual machine managers and for the high-level OS. Application development and debug usually entails yet another level of debug, such as Eclipse Debugger, log files, GDB, and yet others. These debugging efforts can be greatly improved by using a debugger which is OS agnostic and capable of debugging from the lowest level of software to the application space, all through a unified debugging environment. The multi-debugger shown here can handle JTAG, freeze mode debug at bare metal, and enable bring up of the lowest level software in the system. In the same environment, you can perform runtime debugging of the virtual machine manager and virtual freeze mode of the high-level OS, while simultaneously allowing run mode debug of critical device drivers and critical applications, as well as run mode debug of high-level applications. In this example, this is all leveraging a safety and security certified RTOS, which offers virtualization as a service to enable critical applications to run in a safe manner, while also offering virtualization of high-level OS for non-critical tasks. So let's go back a bit to the requirements of a safe and secure critical system. In a traditional single-core safety system, there is, of course, only one core operating. That core has sole ownership of the buses, peripherals, and other resources. It operates small threads which are easily decomposable for safety and security certification. Safety and security are the highest priority tasks within the system, and there's deterministic bandwidth and response time. On the other hand, the common multiprocessor system today entails software with multiple complex threads, shared peripherals, buses, and other resources, and has multiple tasks at multiple priorities, but sometimes with conflicting priority. The shared bandwidth creates inconsistent response time and can therefore remove determinism from safety critical applications. Determinism is essential in safety critical systems. We need a well-bounded response time to ensure that deadlines are hit. Missed deadlines can result in catastrophic loss of safety in these critical systems. Worst case execution time must always be considered when assessing the deterministic response time. The developer must have an in-depth knowledge of the system and all interfering activities on the device. Testing has shown more interfering activity can cause a nonlinear increase in worst-case execution time. In fact, worst-case execution times as high as 8x have been observed on systems with only 2 cores. Here is an example of a 4-core system. If there are no interfering cores you can see that the application runs with an execution time of 1. But when a second core is introduced, thus creating one core interfering with our critical application, the relative execution time goes up to 7x in this case. When a third core is added, the relative execution time goes up to 13x. And when a fourth core is added, we see a 14x in relative execution time. As stated, worst case execution time must always be considered when assessing the deterministic response time. However, that worst case execution time is not always the same as the deterministic response time. Different use cases create very different worst case execution times. This can be very problematic if one intends to add applications to the system later in time. In the example shown here, we have a system which is running 8 applications. We can see that when app 3 is in the system, app 1 has 60% of the bandwidth available to it and has a worst case execution time of 1. However, if app 3 is removed and replaced with app 9, we see that the first app is left with only 10% of the memory bandwidth, and its worst case execution time increases to 9. So in-depth system knowledge should be applied when developing these systems and must be applied to determine proper mitigation techniques. Of course, none of these safety techniques matter if the system is not properly secured. If someone can alter the operation of the system through a security breach, then none of the safety can be assured. Note that the system bandwidth issues we're discussing here today may not be just due to poorly written apps or poorly defined system knowledge. Security must be enforced within the system to prevent improper code from running, whether it is inadvertent or intentional. Rogue applications running on a multi-core system don't even have to break into the rest of the system to create havoc. They can create a denial of service for critical applications by simply overwhelming the shared resources such as memory and buses. A high assurance separation kernel is built on 4 principal attributes required of any such kernel. It must be non-bypassable, evaluatable, always invoked, and tamper-proof. Cross-core memory bus allocation is a very important field of study today as we continue to see more use of multi-core processors. Greenhill Software has over 60 years of R&D in this field, over 60 staff years of R&D in this field. We have developed solutions that monitor interference channels and mitigate such interference from delaying critical applications. This enforces allocation of bandwidth to shared resources for each core based on fixed bandwidth utilization curves and functional requirements of the design criticality for each application. Defined time quantums are created in which maximum allocation is defined for any resource. Libraries are supplied for interference library, DMA generating, bandwidth reporting, and runtime mechanisms. When assessing the bandwidth interference and bandwidth availability, interference profiles are created to model and test traffic on the application being assessed, as well as the other interfering cores. Available bandwidth is dependent on many variables within the system, including the processor architecture and inherent latencies, memory type, clock speed, configuration registers, and interference profiles. This interference can come from the core's own tightly coupled memory, from shared caches between the cores, cache configuration and behavior with the device's memory, DMA activity to and from the peripherals, and of course, individual cores activity with peripherals. When all of these considerations are taken into account, the applications are properly monitored and mitigation techniques are put into place, the results can be very impressive. You can see the results we discussed earlier with the unmitigated interference within a 4-core system. By creating interference profiles for our critical applications and the cores they run on, as well as the other cores in the system, We can then define bandwidth allocation curves to ensure that the critical tasks get required bandwidth to properly contain their execution times. As you can see here, by applying the monitoring and mitigation techniques, we can see a very consistent allocation of bandwidth to critical applications while other applications are running in parallel. With only a single core operating, meaning no interfering cores, you can see on the red line that allocating only 80% of the bandwidth to the critical app shows only a slight increase in worst-case execution time from reduced bandwidth allocation. When the bandwidth allocation is reduced to 50% or even 20%, as shown in the green and black lines, the relative execution time extends accordingly. This solution ensures consistent operation of your critical applications, regardless of the activity on other cores. You can see that with 1, 2, or even 3 interfering cores on a multi-core processor, we can maintain consistent bandwidth allocation and worst-case execution time for critical applications. When the system is integrated and necessary bandwidths are assigned to the critical applications, you can be sure that the required bandwidth will always be available to that critical application, regardless of the interference caused by other applications on these multi-core processors. The impact of this solution is reduced risk, simplified development, reduced size, weight, and power of your final solution, creation of spare compute capability for future updates, eased certification for these complex multi-core systems, and of course, improved time to market. Thank you.